In this video, we are going to understand the concept and some questions related to the chapter Electricity, class 10th. Now, before that, we need to be familiar with some uh, key terminologies. Now, the first is the charge. By definition, charge is a fundamental particle of an atom, and it may be positive or negative. Now, when we use the word charge, it can be either electron, that is negatively charged, could be an ions also, like Na plus or Cl minus. But we need to remember here that when we talk about ions, the ions are responsible for the flow of current in an electrolyte, while electrons are the charged particle which are responsible for the conduction of electricity in a metal, including mercury, which is in the liquid state. We have already done these things that like charges repel each other and unlike charges attract each other. Now, this charge is actually measured in a unit called coulomb. Like there's a unit of charge is coulomb. And if we figure out the number of electrons present in 1 coulomb is approximately 6 into 10 raised to the power 18. Well, exactly it is 6.25 into 10 raised to the power 18 electrons, but we approximately write like this. Moreover, what you have studied already in class 9, that the charge on an electron is 1.6 into 10 raised to the power minus 19 coulomb. Now, sometimes you may be asked to calculate the number of electrons present in 1 coulomb. Well, over here, we know that 1 coulomb is equal to 6 into 10 raised to the power 18 electrons, but we can be asked to calculate the number of electrons. For that, you have to remember this. So I'm going to calculate it. What you're going to write here that you can write from here that 1 coulomb comprises of, 1 electron has a charge of 1.6 into 10 raised to the power minus 19 coulomb. So we can write in a reverse way that 1.6 into 10 raised to the power minus 19 coulomb will have 1 electron. Now, using unitary method, if I write 1 coulomb, then I have to transpose this on the other side. It's 1.6 into 10 raised to the power minus 19 electrons. Now, if I write in the standard form, like removing this decimal from here and transposing this exponents to the numerator, we get something like this. I can reduce it by 5 times to 8 times. Further, if I take 110 from here, it becomes 50 into 10 raised to the power 18, that divided by 8. If I reduce it, I'll get 6.25 into 10 raised to the power 18 electrons. As I said, we may be asked in the exam to calculate. So when you are asked to calculate, you cannot just say the numbers. You have to show that how we are getting 1 coulomb as 6.25 into 10 raised to the power 18 electrons. Now, if I talk about the relation here, so it's very clear that is the charge will be equal to the number of electrons, that is n is the number of numbers here, that's the unit of electron. So number of electrons into this charge on electron. Now coming to the next, that is current. In class 8, you have studied about static electricity. Now we are studying current electricity. So they are different, and the different lies on the sense that current here means in motion. So by definition, we say that, let's say if I take a conductor here, I took this conductor and these are the charged particle. Let's say I'm taking the charged particle. Now, these charged particles actually are in motion. These charged particles are in motion in a conductor. That is, the charged particle here is the electron by default. So these electrons are in motion. That's why we see current electricity, unlike static electricity where the charges do not flow. So the definition of the current comes from this only, that it is the rate at which the charges flow. That means how fast or how slow the quantity of charges flows through a conductor is what current. And that's why the definition of current, as I said, the relation here is current is equal to charge over time. So once again, current, which is denoted by its SI unit, its symbol is I, is amount of charges, right, that flows through a conductor in one particular unit of time. And you also have to remember that is we measured it through the cross section. Like say, if you know that a conductor like a wire generally are cylindrical in shape. So if I say that the cross section of this is over here could be anywhere. Say I took it here. So we can say that the number of charges, let's say once again, take the same charges here. These charges, the number of electrons that is passing through this particular cross section area in 1 second will be called as the current. Now, if we further, as I said, the SI unit we have to calculate, but the relation first you have to remember that I is equal to Q over T. Now we are going to figure out what should be the unit of current, whose symbol is I. So we know that I will be 1 unit if I take charge as 1 coulomb and time as 1 second. So we can figure out 1 unit of current will be when 1 coulomb of charge, well, 1 coulomb is what, 6.2 into 10 to 5 into 10 raised to the power 18 electrons. So that much electrons, if it flows through a conductor in a one cross section area section of wire in 1 second, that is equal to 1 unit of current. So we can say that the unit of current could be 1 coulomb or coulomb per second, which is also called ampere, which is also we use the symbol ampere. Sorry, symbol as A and it is ampere. So SI unit of current is ampere. So ampere measures the current in a conductor. Ammeter measures the current in a conductor. Ampere is the unit in which it is measured. Now we have even smaller unit, as you know that when V current flows through it, we cannot use the unit ampere. So you should remember that there is a milliampere and microampere. Milli stands for 1000 relation. That means when 1 ampere is actually 1 ampere is divided into 1000 parts, one part will be equal to 1 small m and capital A, right? So this is a relation. Well, we will be using this only, that 1 milliampere is equal to 10 raised to the power minus 3 ampere. In short, if you have to compare ampere into milliampere, we are going to multiply by 1000, as you must be knowing that converting a bigger to smaller unit, we multiply, and vice versa. That means when you have anything in milliampere and you want to convert into, in general, we use this only, we divide it by 1000. And same way, you can also get a relation with the micro amp. Sorry, that's, yeah, this is micro or nano. No, this is micro. This is microampere. Nano ampere is Na, which is 10 raised to the power minus 9 ampere. Anyway, this is not something we have to study in this class. We have to know these two relations. Now, as I said that there's a device that can measure the amount of current flowing through it, and the device is called ammeter. Now, in this physics, we do not actually draw the diagram of that device, that how does it look like. We use symbols. We use symbols like you have studied in lower classes about the symbol of a bulb, and similarly symbol of a key. Key can be two. This is an open key. This is an open key, and this is a closed key. Right, and the keys has other diagrams also, other symbols also like this. So similarly, we have a symbol for ammeter. That's very easy. Just have to write A here, so encircle it, put a circle in over it, and so two terminals of the wire, show one end of it as positive and the other end as negative. Now, this ammeter, as I said, is a device, and there is a proper way of connecting this device. Now, at this stage, you may be not able to get clear with these terms here. That is, what is resistance stands for, and what is series, or other way. There is another way of connection called parallel. We'll be studying this in the later part of this chapter, but just to understand this a bit, you can remember that resistance is what the characteristics of a conductor which resist the flow of charges. That means lower the resistance, the smoother the current will flow through it. Just like if there is a traffic flowing and if there is a more this if the road is smooth, the traffic flows smoothly, and if it is not good, then wear and tear takes place and the wa- vehicles does not move smoothly. Anyway, that's very easy to understand. Resistance, as I told you, we'll be studying it later in detail, but for now you can see, remember that it is something which resists the flow of current. So lower the resistance, smoother the current flows through it. Now coming to the next term, series. So as you can see, like if I have to connect devices, like say for example, I'm taking two, three devices, maybe these are any device, could be bulb or anything, and I connect them through a battery. If I connect them through a battery, let's say this is a single cell, that will be fine. And now you can see that these devices are connected end to end. Now such type of connection like A, B, C, D, these devices will be say they are connected in series end to end. Well, we have another connections called parallel. We'll be studying, as I said, in detail some later part of this chapter. Now, if I take three devices and I connect them through a battery, let's say I'm connecting them through a battery. And as you can see, if I connect them through a battery, like they are independently connected with each other. So that's why they are called parallel. Well, it is slightly different from mathematical series and parallel thing. Geometry, whatever you study in parallel in geometry will be slightly different. But let's come back to what we are talking about. The ammeter, which I said is a device, and this device always has to be connected in series. And these devices have low resistance. So let's say, for example, if I make a circuit here and if I have to plug in or put one ammeter, then how should I place it? Let's say first I make a battery here. The longer one stands for the positive terminal, a gap over here, then connected with another positive terminal, and negative one is this. So this is positive, this is negative terminal. But over here, I'm concerned about making an ammeter and to show you how this ammeter is connected. So this ammeter is always placed in series. As you can see over here, this placed in series. This is a connection in series. Now, another important concept over here is the direction. As you know, electricity is a physical quantity, and in physics, we always consider about the magnitude and its direction. Now, the direction of current, if I take this as positive and negative terminal, the direction of current is taken opposite to the flow of electrons. Let's understand the history of this. Initially, when current was discovered, the scientists did not know what is the cause for the flow of charges or which is responsible for the flow of current. So conventionally, like all the scientists universally decided that they are going to take the direction of current from positive to negative. So they took the direction of current as this. That means direction of current was taken conventional direction, right? Conventionally, which is universally accepted. So this is what the direction of current was taken. That is from positive to negative terminal. I repeat, we are not talking about the electrons here. We are talking about the direction in which the current. The direction of current is taken from positive to negative terminal of the battery. But later on, when they discovered that it is the electrons which are responsible for the conduction of flow of charges, and electrons flows from negative to positive terminal of the battery. But then they decided, because changing this direction would have changed, has to change, bring about changes in other theory also. So they decided that we will continue to take the direction of current as positive to negative terminal of the battery. That is the reason whenever you are asked about what is the direction of flow of charges, just do not say that it is from positive to negative. Say that we have to use the term conventionally, the flow of direction of current is taken from positive to negative, which is opposite to the flow of direction of current, direction of electron. One more time, direction of current is taken opposite to the flow of electrons, that is from positive to negative terminal of the battery. And we need to use the term conventional. Like conventional, it is taken from positive to negative terminal of the battery. So I've taken few questions just to recollect what we have done here. So in this question, it says that an electric device which draws a current. The symbol of current is I here. So it will be I is equal to 1.5 ampere and is kept for 4 hours. So time here, time can use capital T. It's a small only. Time, SI unit of time is seconds. So I'll be multiplying 4 with 3600. So this is the time here. So this is 6 into 4, 24, 4 into 3, 12. So this much second. Now, what is the charge flows? So we just derived one relation here that although we remember that I is equal to Q by T, but it is easier to remember Q is equal to IT, right? For the definition we obtained from here, but it is easier to remember this one. Always you remember this one, irrespective what you are asked, whether you are asked to calculate I or T. Now, using this relation, I can say I is equal to Q is equal to I into 2T. So it's 14400. So if I use a calculator to get it, so it's 21600. Do not forget to write C, that is stands for the coulomb. So we'll say that C is the correct answer. Now, next is an electric current is measured. So voltmeter is used to measure potential difference. We just studied about ammeter. It's a device which is used to measure the current. Another question here is if the net charge is Q that flows through a cross section of a conductor in time T and I, so we have to find out the relation. We have just get to know that Q is equal to IT. When I see this is not an option, we will go for I is equal to Q over T by transposing. So I is equal to Q over T. So this is what. So I stands for the current, Q stands for the quantity of charge, and its unit is coulomb, T for time. You have more question, I suppose? Yes. In this question, it says that if the amount of current flowing through a conductor is what we have to calculate, and the amount of charges that flows is 300 in 10 minutes. So let's write symbolically Q is 300 coulomb. We have time is equal to 10 into 60. So that comes out to be 600 seconds. So applying the relation I is equal to Q over T, that implies I is equal to Q, which is 300. That divided by time, which is 600, clearly is half, or we may write 0.5 ampere. So this would be the correct answer in this case. So the question next is, then electric current is passed through a metallic wire. The particles, I just told you that in a conductor, right, it is the electrons which are responsible for the flow of current, right? Although ions are also charges, but ions are responsible for the conduction of electricity in electrolyte. You might have remember that acid, bases, salts, they conduct electricity. Like if I put some copper sulfate solution here, and if I put 2 electrodes connecting them with a battery, right? If the current flows through here, then it is here the electrons are not responsible. Like if I take copper sulfate solution, then as an electrolyte, so it's ionized into Cu2 plus and SO42 minus. So these are responsible for conduction of electricity in electrolyte solution. I'm talking about ions here. But in case of conductor, it is the electrons which are responsible for conduction of electricity. Further, you should know that even if the metal, like in case of mercury, mercury is in the liquid state, right? So in that case also if there is a flow of charges in mercury, then we'll not say it is ions, it is electrons. Ions are for ionic compounds. And the next question, it says an instrument called DAS is used for measuring electric current. We just did. It is ampere. Well, ampere is used, and it is always connected in series. So therefore, this is the correct answer. So next is a stream of electrons moving through a conductor. That's electric current. Stream of electrons. But when an electrons is static like this, let's understand one more thing. I can say I took a copper rod, or say anything like this, or conductor. So this is metallic conductor, maybe silver or iron or any good conductor. Now there are charges, right? There are charges here. But these charges, if I touch this conductor, I will not get an electric shock. Or if I connect a bulb or any device, it will not glow, even when the charges are there. So these charges has to be in motion for the current to produce. That's why we say that moving charges, the charges has to be in motion and not in random or haphazard direction or in a zigzag path. It has to be in one particular direction from one to another end. That's what it means, the stream of moving conductors, moving charges that constitute electric current. Now, next we have to identify which one is the incorrect statement. Well, the first is the direction of negative charges is taken to be the direction of current. Well, negative charge is what? Electrons. Negative charge here are electrons. But we just studied that it is the opposite to the direction of negative charges. So this is an incorrect statement. The SI unit of electric charge is coulomb. We have to find incorrect, and there should be one incorrect only. So we'll close the answer here only. Incorrect statement. Yes. Now next is the electric current circuit, the direction of electric current. So I didn't tell you the circuit. What does it mean? So this is circuit means the closed and continuous path. Like say I took a circuit where this I'm placing for something, some devices. Let's say, for example, I place a bulb here, maybe a battery or a cell. So combination of two or more cell is called a battery, right? In a right order. And let's say I place a switch here and maybe an ammeter. So the closed, and as you can see here, this is closed, right? This is closed and continuous path. Right? There is no breakage. These are closed. Even the switch is in on position. If it is off, then we say it's open circuit, right? And here the current will pass through. It's a closed and continuous path through which the current flows is called circuit. And this circuit may be open or closed, as in you can see the switch is on. So this is a case of closed circuit when the switch is off, or if there is any breakage of the current, maybe because of wires not connected properly, then we say it's a open circuit. So let's come back to the question here. And in this question, they are asking an electric circuit, the direction of current. That's always from the direction of current is taken from opposite to the direction of flow of current, and the direction is from positive to negative terminal of the battery. So let's one more time. If I make a circuit, it's a very important concept. And let's me make one cell. If I take a cell here, gap for a cell, maybe a bigger line indicating. Okay, let's make one small cell. All right. So the longer one stands for the positive, the shorter one, it should have been short. One more time. Right. So this is positive and this is negative. The direction of current is always from positive, like this is the positive terminal, positive to negative terminal of the battery. So the number of charges present in 1 coulomb, we have already derived it is 6 into 10 raised to the power 18. Now, if you come across somewhere 6.25 into 10 raised to the power 18, do not discard this option. This is also correct. In fact, this is more accurate. Approximately, we write this. In the next question, it says the current of 2.5 ampere is drawn by a filament of the bulb for 5 minutes, the amount of electric charges that flows through it. So the amount of electric charges, but that is Q, which is equal to Q is equal to IT. Well, QI is 2.5 and the time is 5 minutes. Well, 5 minutes in SI units is 5 into 60. So this is 2.5, 6 into 5 is 30. So it's 300. So we'll say 300 into 2.5. So it will give you 750. Do not forget to write the unit. It is coulomb. C stands for the coulomb. This is the correct answer. So next is we have coulomb given here symbolically. I can represent this is 0.5 C and the duration for which the current is flowing is 2 seconds. We have to find the magnitude of current, that is I is equal to question mark. Well, still we'll be writing Q is equal to IT because this is easy to remember and isolate I so as to get the value of I. So I is equal to Q over T, which is 0.5 over, that's 2. So that's equal to 0.25 ampere. Another important question, this one. It says the current of 1 ampere is drawn by a filament of the uh, bulb. The number of electrons passing through the cross section of the filament in 6 seconds. So we have to find out the number of electrons and not the charges. Well, we know that if we know the charge, let's say I get to know the charge as, say, for example, 7 coulomb, right? 7 coulomb. As you know, we know the number of particles present in 1 coulomb as 1.6 is 1.6, no, 6 into 10 raised to the power 18 electrons. Like this is a very simple thing. Like if you're asked to find out the number of bananas, but you know the number of dozens, so you can calculate first the number of dozens and multiply by 12. That's what the concept we are going to apply here. So we know that it is the current here is 1 ampere and time is 16 seconds. So we'll have to get Q is equal to IT, although we have to get number of electrons, but first we'll get Q. Q is equal to IT, 1 into 16. So Q is equal to 16 coulomb. This is coulomb. Now we know that 1 coulomb has, we'll write its accurate value, 6.25 into 10 raised to the power 18 electrons. So in 16 coulomb, the number of electron is 16 multiplied by 6.25 into 10 raised to the power 18 electrons. So this is 625 into 16 should give you, that is 625 into 16, that's 10,000. So it's coming, if I multiply, let me once again confirm 6.25 into 16. And that's, yeah, that comes out to be 100, replacing this decimal, and this is 10 raised to the power 18. Well, if I look into the options here, we can figure out that it is same as 10 raised to the power. This is 10 raised to the power 2, and this is 10 raised to the power 18. So that comes out to be 10 raised to the power 20. That much number of electrons are there. Well, we have already studied that it is the electric current, the definition of electric current, the amount of charges flowing through a wire per unit area, that is the cross-section area. So it's nothing but the rate of flow of charges. Now, how many electrons are there in 1 microampere? So we know that 1 ampere is what? 1 ampere is 1 coulomb into 1 second. And if I say that what is 1 milliampere, then ampere has to be divided by 1000, right? 1 milliampere. So it's 1 coulomb into 1 second divided by 1000. Once again, 1 milliampere is actually 10 raised to the power 3 amp, 10 raised to the power minus 3 ampere. So we can say 1 coulomb into 1 coulomb into 1 second. So 1 coulomb has how much? 6.25 into 10 raised to the power 18 electrons. That divided by 1000. 1000 is what? 10 raised to the power minus, sorry, 10 raised to the power 3. If I apply laws of exponent here is 6.25 into 10 raised to the power 15 electrons. Now we have an option. Next is how many electrons are there in 10 coulomb? Very easy. 1 coulomb is 6.25 into 10 raised to the power 18. Then 10 coulomb will have 10 multiplied by this. And if I multiply 10 over here, 10 over here is going to be what? 6.25 into 10 raised to the power 19. Now we have an option here. Define current. So electric current is what? The rate of flow of charges. Rate means how fast or how slow it is. Then we have to write down the relation between the current, the quantity of charges, and the time. So I can say we have Q is equal to IT. Well, you won't get marks deducted if I write I is equal to Q by T. They're just asking for the relation. Write the relation between coulomb and ampere. So coulomb, like if I replace Q with its unit, that is C, I with its unit, that is SI unit A, and T by with its seconds. So I can say like this. It's better to make changes over here. Let's say this is I, this is 1 coulomb over 1 second. So that's what. That's done. Now next is state the relation between the current passing through a conductor, the number of electrons taken as N. So we know Q is equal to IT, or I is equal to Q over T, and Q is what? The quantity of charges. The quantity of charges, quantity means number, and the charges is the electron. We may not give a minus sign. So I can replace Q with this thing, that is NE and over T. Next is define 1 ampere, where this is an important question, has been asked several times in exams. So in order to find out 1 ampere, let's write down what is current is equal to I is equal to Q by T. We know that this will become 1 unit provided Q is 1 unit. That is 1 unit of Q is 1 coulomb, and 1 unit of time, say 1 second. So now we can define 1 coulomb, sorry, 1 ampere. 1 ampere is what we 1 ampere is the current flowing through a conductor when 1 coulomb of charges flows through it in 1 second. One more time. 1 ampere is the current produced when 1 coulomb of charge flows through a conductor. That's a current carrying conductor, not any conductor. So current carrying conductor in 1 second, then it is equal to 1 coulomb. As it is important, I should say the model answer that I've written. Yeah, if 1 coulomb of charges flows through the cross section of a conductor in 1 second, that is equal to 1 ampere. Direction of electric current related to the direction of flow of current. That's very simple. Direction of current is taken opposite to the direction of flow of electrons. Electrons flows from negative to positive terminal of the battery, while direction of current is opposite. That is opposite to the flow of electrons. How is ammeter connected? Ammeter, this device, I told you that this ammeter device is always connected in series. Well, there are two types of connection. Only two types of connection is there in electricity. So this device ammeter is always connected in series. Once again, there are two types of connection. One is series, another is parallel. We haven't came across the parallel connection, but series is this. Based on same concept. It says by what physical quantity coulomb per second. So coulomb is charge and time. So that is charge over time. That is I, which is physical quantity we are saying. So we'll say current is that physical quantity. What actually travels when wires or through the wires when you switch it on? So it is the electrons which travel or flow. As I told you, the conventional direction is from positive to negative terminal of the battery. And electrons flows from, sorry, conventional is from positive to negative terminal of the battery, while electrons flows from negative to positive terminal of the battery. Next is how milliampere is related. I told you milli is this, right? Milliampere. So I have to write ampere in terms of milliampere or milliampere in terms of ampere. That's all same. I mean, you may get marks in any case. So 1 milliampere is equal to 10 raised to the power minus 3 ampere. And similarly, 1 microampere. The micro symbol is this. Ampere is equal to 10 raised to the power minus 6 ampere. A current is a flow of charges, right? For this to happen, there must be dash. Current is measured. Okay, this is based on the concepts which we have not studied. We'll study about this in the next section because I'll be used a term that potential difference and a battery. Well, still, I think you can get it. A current is a flow of charges. For this to happen, there must be a source of current, and the source here could be a battery or a cell or an electric generator. Current is measured in ampere using a device called ammeter, and that is placed in series. This question also has the same thing, which we have to write down the formula. Once we have written I is equal to Q by T, then they are asking you that calculate the amount of charges, that is Q is equal to IT is what we have to get. Here I is given as 0.36 and the time for which is 15 minutes. Yeah, 15 minutes is what? 15 into 60 that you can calculate. In the next, it says an electron, which if the charge on an electron is this, fine. How many electrons should pass through the conductor in 1 second to constitute 1 ampere? Well, as I said, we are asked about electrons, but we always go for coulomb and then convert it. So Q is equal to IT. So Q is equal to I is what? I is 1 here, 1 ampere given. And the time is also 1 second. So Q is equal to 1 coulomb. Now, once we obtain 1 coulomb, I can convert coulomb in, convert the coulomb in, this is C coulomb. And 1 coulomb is 6.25 into 10 raised to the power 18 electrons. So I can replace 1 coulomb with the number of electrons, which is 6.25 into 10 raised to the power 18 electrons. Same in the next question, I can see how many electrons. So number of electrons, as I said, whenever it is asked, we always get the number of coulomb. So Q is equal to IT. This question Q is equal to I is 5 ampere and per second, that means 1 second. So Q is equal to 5 coulomb. Once again, 1 coulomb is 6.25 into 10 raised to the power 80 electrons. So if I replace this C with its value in terms of electron is this. So we can multiply to get the answer. What is meant by electric current? So electric current is the rate of flow of charges. Name and define its SI unit. Its SI unit is what? Its SI unit is ampere and define is what? 1 ampere. 1 ampere definition is when 1 coulomb of charge flows through a conductor in 1 second. In a conductor, electrons flow from B to A. So electrons flow from B to A. B to A, and electrons flow from negative to positive terminal of the battery. What is the direction of conventional current, it should be from A to B. Justify your answer, and the justification is that the direction of current is taken conventionally opposite to the direction of flow of current. I think there is one more below this. And what is it? A steady current of 1 ampere flows through the conductor. Calculate the number of charges based on the same question that we have done several times. So let's say I end this over here only. And in the next section of this video, I'll continue with the potential difference. That is the next thing we have to study in class 10th in order of physics electricity chapter.